Hello, you're welcome back. All right, now we'll continue from where we stop. Okay, we are going to be discussing complex numbers. Okay, in this particular video. All right, now what's a complex number? Okay, so a complex number is actually a number. Okay, that is made up of a real number and an imaginary unit. So that is why it is called complex. All right. You know very well that we are familiar with real numbers that is used, okay, to express quantity. For example, we have real numbers that actually ranges from have the zero and the positive numbers one, okay, two, three, four. You get you alongside with some other number in between, okay, decimal numbers till you get to infinity. Then you now have the negative numbers starting from -1. Okay, these are numbers. We can use them for counting. They are all real numbers, all right? You can use them for counting and we can also use them to express quantity. So, but when a number doesn't just, okay, contain real number, it also contain another part of it, another part that's attached to a real number, known as imaginary unit. It becomes a complex number. And that complex number is really very important when we are dealing with alternating current. Why? Because in alternating current we are not only dealing with magnitude, all right, as we already know. Alternating current don't just deal with magnitude, we also deal with direction, like vector quantities. Okay, vector quantities in which you don't only deal with the magnitude, you also have to deal with that direction, all right. So now let's talk about the J operator. Now we use the J operator to represent the imaginary unit of a complex number. Okay, so invariably now I can express a complex number in terms of a J operator. Let's say a complex number A, all right, is equal to 20, and I have J. So discover that the 20 is the real number, while the J now is the imaginary unit. The J is the imaginary unit of the complex number. Okay, so we'll talk more about J now. The same thing you've already learned, okay, when you treated complex number in mathematics, that is what we have here. Though in mathematics we use I as the imaginary unit, but we want to actually, here in alternating current, we're going to be using J so that we will not confuse the I for current, okay? Because we've already, in electricity, we've already specified I for current. That's why we now use J. Okay. So now, as I said, J is an imaginary unit, and of course, you know very well that J, the origin of J is actually equal to the square root of -1. Okay. Of course, if you have not gone through the tutorial of complex number, okay, I think if you go to the algebra, go to our algebra resources, complex number is there. You can actually go through that tutorial, okay, one more time, then you understand complex numbers. Okay, J is equal to -1. So in which, if we actually evaluate J square, it gives us J is equal to the square root of -1. Please pardon me. Okay, so if I should evaluate J square, you're gonna give me -1. Okay, if I evaluate J cube, J cube, of course, you know what it is. It's going to be J square multiplied by J. So since J square is already -1, so I'm going to have -1 times J, that's going to minus J. If I have J raised to the power of 4, of course, you know what that's going to be, okay? So J raised to the power of all 4 is going to be equal to J square, then all square. Now J square is minus 1, okay? Now when I square it now, it's going to be equal to 1. Okay, so these are the powers of J, right? So anytime we are manipulating J, this is how we actually manipulate the powers of J. And of course, now the question is, what does J represent in alternating current? I said that J is an imaginary unit which represent the phase, okay? Because anytime we are dealing with an alternating current, there's always a phase. The J will always represent a phase. Okay, for example, we know very well that um, in alternating currents that has alternating current circuit that has the inductor, the capacitor, and of course the resistor, okay, connected is connected in series. Connected in series, okay. All right, of course, this is my inductor, this is my capacitor, this is my resistor. We already know exactly how voltage vary here, okay. So the VRMX, the supply voltage, is going to be equal to the voltage across the inductor plus the voltage across the capacitor and plus the voltage across the resistor, okay. So now we see that all these voltage, they have their phase angle, all right. So we can actually represent them, okay, in a phasor diagram. Now there's another way of representing them, okay. We can also represent them in a complex number. What I mean, what do I mean by complex number? Complex number, the J operator is always, okay, plus J operator is always vertical, okay. So any component, okay, whose parameter has plus J operator will always be in the vertical y-axis. This is minus J operator, and this is J. There's no operator here. This is 0 J operator, okay. Horizontal, that is for the resistor. So resistor doesn't have any J operator attached to it. So invariably now, if I'm dealing with voltage, okay, that simply means that I will attach J to the voltage of plus J, okay, to the voltage of the inductor. All right, why? Because the phase angle is positive 90 degrees. So we use J to represent phase angle, of course, of, please take note, the J operator, okay, let me write it down. In alternating current, the J operator in alternating current actually represent the phase angle of 90 degrees, okay, that phase angle of 90 degrees. So that's positive J is going to be positive 90 degrees. Why negative J, all right, is going to be negative 90 degrees. Okay, so coming back to our vector diagram. Okay, so the voltage of the inductor is positive J, that's plus J VL. Then, of course, the voltage of the capacitor is negative J, that's going to be minus J VC. Okay, then, of course, the inductor doesn't have any J, it's actually 0 J horizontal. Okay, so what does that actually imply? With this now, you can actually get the total voltage by summing the voltage. So in this case, the VRMX is going to be the sum of the positive J, okay, let's start with the resistor, which is the real number. Resistor is the real number, it doesn't have any J attached to it, okay. Then plus that of the inductor, that of the reactance, please pardon me. Okay, so please I'm dealing with V now. So VR, the voltage of the resistor. Okay, then plus the voltage of both the inductor and that of the capacitor. Okay, they are opposite. So that's gonna be J bracket open VL minus VC. Of course, you know how I got that. Let's do that again. Of course, you know how you add it. Okay, you add plus J VL, and of course minus, this is minus J VC. Okay, so that means the VRMX now, the source voltage now is going to be equal to VR, voltage of the resistor, which is a real number. It's not a complex number. It doesn't have any J attached to it. Then I factorize J out. Then I'm going to have VL minus VC. Okay, so this is how I use the J operator to actually represent, okay, the voltage across these three components: inductor, capacitor, and resistor of an alternating current. You can also I can also use it to express the impedance. Of course, you know, for the impedance, okay, we deal with the same diagram. Okay, works for the impedance. For the impedance now, all I just need to do is to replace the VL with SL. You know that already. Okay, for the VC, I replace the VC by XC. That is capacitive reactance. Okay, and of course this one is just resistance. It's not a reactance. So if I should write it now using the J operator, so I want to have the resistance, then plus J bracket open SL minus XC. Okay, so this is actually the representation, the vector equation. You can call it vector equation or phasor equation, okay, of an alternating current, okay, by introducing the J operator that actually shows me the phase angle of any of the components, okay, either okay either um either for the voltage or that of the impedance. So it's just a very simple. It's what you are going to be doing here is what you've already done before. Okay, so I don't need to emphasize on that. I will actually encourage you to go back to the complex number, see how we work on I operator. Okay, go to the mathematics part of this particular resource. Then you go to algebra, you see complex numbers, go to complex number tutorials. All right, so everything we are going to be doing here definitely will have x, the operations and the simplification is what we've already treated before in complex numbers, okay, in algebra complex numbers. So you can actually do that. Now when you now come, let's see, we're going to see how we apply complex numbers, okay, to the resolution of alternating current circuit parameters. All right, okay, so I'm going to give you the opportunity to do that now, then we'll continue in the next video. All right, see you in the next video. Thank you very much.